Welcome back. This is part two of the April 6th set of videos. Let's go back to our Jupyter lab. Okay. Oops, open a new tab. Go back here. Yeah, there we go. Okay, so this is where we were. Last time we just had wrapped up higher order functions, basic, and then we showed how that example of summing f of a, f of a plus 1, f of a plus 2, and so on up to f of a up to f of b. Okay, we talked about how we can make a generic function called sum, which will actually do all these things for us. Okay, all right. Now the next example is to do with products. Okay, somewhat like sum. Okay, and actually very similar. Okay, now remember the factorial. We had some issue in the last example. We were able to uh, provide an unnamed version for ID and also an unnamed version for cube. But we made a comment that factorial unnamed version is a little tricky, right? Because there's a recursive call, so it's that we'll have to deal with that. Okay, but anyway, this example goes about and defines a similar function like sum called product. Okay, all right. So let's look at the code here in this particular cell. The first one is the same as what we had before, the sum of a and b. Now this is without the higher order function. Okay, yeah, it just recursively calls on the next one and so on. So this is the original sum of integers between a and b. Okay, all right. Now let's say that we instead of adding numbers, we want to multiply the numbers. Okay, uh, like a times a plus 1 times a plus 2 times a plus 3 until b. Okay, simple enough, right? So the code, the body of this function will change slightly. If a greater than b, then the answer would be 1 rather than 0. Okay, because we had to otherwise if you say 0 here, then the answer for everything would be 0. Okay, because 0 times anything will make it 0, right? So 1 is the identity for multiplication from mathematics. Okay, so that's why we say 1 here instead of 0. Okay, and then in the recursive part we say it's a times product of a plus 1 comma b. Okay, so this will keep on multiplying recursively, okay, until it reaches the 1, and at that point we'll multiply by 1 and we get the answer. Okay, and now if you recall, the factorial is nothing but a product of 1 through n, right? N factorial is n times n minus 1 up to 1, right? So the factorial function can be rewritten in terms of product as follows. Okay, factorial n is input and output is integer, and you just make a call to the product and give 1 comma n. Okay, got it? So here we have now a product function, and then also the factorial defined in terms of product. Okay, all right. Now you'll see that we are actually trying to generalize the previous idea beyond the sum. Okay, so we want to generalize it to sum and then now to product as well. Okay, so here's okay, this piece of code, the object is something we are not going to emphasize too much. Okay, because we are not learning object-oriented programming in Scala, we are learning functional programming in Scala. So I won't give you too much explanations on what all this is about. You see, focus your attention on the functions inside. Okay, but I mean, if you do want to play around with object-oriented Scala, hopefully at some point in time beyond the class, you will be needing or using Scala. The object is like a class, except that it defines. So so for example, if you have a class which does not create objects out of it, you see. You know what I'm talking about? In Java too, these are called static classes. You see, static classes. Okay, the classes which are just there. For example, the math class in Java, java.math, it's a static class which encapsulates just a whole bunch of functions. That's about all. Okay, so that's what is this one here, object. Okay, so instead of this object, if you say class, then it becomes the traditional class out of which you can create objects and so on. Okay, but anyway, let's not spend too much time on that. Okay, but in general, when you have a bunch of functions, you can put them together into an object like that. Okay, and the object can also have the main function, so you can actually test those other functions you're writing here with the main function. Okay, so this main looks very much like the main of Java. Okay, slightly different in how you write this parameter. In Java, we had to say string argb, right? An array of strings is what we have to do. So this is how you do array of strings. We haven't learned arrays yet. It'll come in later parts of the Scala. But right now, just assume that this is the array of strings, the command line arguments. Okay, and this args is never used. You can see that. Okay. Anyway, so this piece of code has got 3 functions defined inside that. Okay. So you can see that the sum and the product, these 2 functions sort of similar things, right? They all begin with A. Both these begin with A, and actually at this point we're not complicating it further by applying a f of A, that is a cubing or whatever. Okay, we're not doing that. Okay, so we're just going back to the original problem where we just have A through B, and in the first case, in the sum, what we're doing is we're just adding the numbers A plus 1, A plus 2 up to B. Okay, in the product we're multiplying, but other than the fact that we're multiplying and adding, the rest of the code looks similar, right? Very similar structure. Okay. Oh, one other difference is that the identity here is 0 and then the identity here is 1. Okay. So other than those 2 things, okay, one is that the identity is different, the 0 here, 1 there, and then the operation we are performing is plus here, and then here is multiplication. Okay. Other than those 2 aspects, these 2 functions look the same, right? And whenever you see such a pattern where 2 functions look the same, except for some slight variations, you can actually generalize and make one function out of those 2. Okay, and that's really what we are showing here. Okay, so you can see that the sum, and so inside this sum product example, okay, let's look at this operate function first. Okay, and then we will see how sum and product become special cases of operate. Okay, so here's an operate function. Operate is the name of the function. Takes 4 parameters. Okay, got it? The A and the B from the original idea. We must start at A and end at B, right? Those 2 are still there. It takes 2 other parameters. Okay, the F is one of the parameters, and this F will encapsulate that plus or the times. Okay. This F is a little different than the F which was used in the previous example, which was F of A. Remember? F of A, like the cubing or the factorial and so on. No, this F is also a function. This one takes 2 integers as input and 1 integer as output, whereas the previous one was taking only 1 input integer and 1 output. The cubing, for example, cube, and so on. Okay, so this is also a function, but a different type of function, f. Okay, which takes 2 inputs and 1 output. Okay, 2 integers input and 1 integer output. And the idea behind this f is that it'll encapsulate, or it'll capture the plus and the times. Okay, all right. So that's the f. So f is going to be either a plus or a times function. Okay, or something else which takes 2 numbers and then produces a output. Okay, like a divide. Okay, or a minus or something like that. And the second parameter here to operate is called ident, which is this identity value. Okay, this 0 or the 1. Okay, because those are the 2 variations in sum and product, right? The identity and then the actual operator, right? So, and those 2 we parameterize. Okay, with these 2 parameters, the f and the ident, and then the a and the b remain the same as before. Okay, so that's the operate function, and it takes these 4 parameters, operate, and then returns an integer as output. Okay, which will be the final answer for the sum or the product. Okay. All right, let's look at the code. Code again seems pretty straightforward in the sense that it's going to look like either of these 2 lines. Okay, it has to look at like similar one of those 2 lines. So it says if a greater than b. Here it was 0 and here's 1, but here we'll say ident because we don't know whether it's 0 or 1. Okay, right? So whatever is the value provided here is what we'll use as the identifier there. Not identifier, but identity value. Okay. Else, okay. Else here it was a plus and a times, right? So here the plus and the times has become a variable f, right? So we have to say f of a So A is the first value input to F, and then F would be either a plus or a multiply, right? We're hoping F would either be a plus or a multiply. And if F is a plus, then this will be A plus something. Okay. If it's multiply, then it will be A times something. Okay. And what is that something? It is actually a recursive call to operate with the same F, with the same identifier, but with A plus 1. Okay. So basically go ahead and do the same thing, but starting at A plus 1 and get an answer. And then whatever answer you get, you either add it to A or multiply it to A, depending on what F is. You see? Got it? All right, so this function here, operate, has become a very generic function, but it does take 4 parameters, but it allows you to sort of combine the ideas behind sum and product into one function, okay? And not necessarily those two. Now you might want something for divide and something for minus and so on, okay? So, but you get the idea, okay? That we are generalizing patterns in functions which are similar patterns, and then we create a new function out of that. Okay, so that's the operate function. Okay, now what will sum look like? Sum will just be a call to operate. You see, right? The previous sum was not a call to operate, but now this sum will be a call to operate. And what it does is that it provides the function f. You can see that x, y, arrow, x plus y. So this is the plus function. Okay, or the addition. Okay. So x and y are the inputs, and x plus y is the output. What is that function? That's the sum function, right? It takes two numbers as input and produces the sum of the two as output. Okay, and here's the identity value for the plus, which is a 0. Okay, and then the a and the b we provide as it is. You see? So this function sum operate, whose body is this operate line. Okay, and if you look at the product, which is also has a similar operate line, the only difference is that the function here is x times y instead of x plus y, and then the identity is 1. Okay, so now these two functions, sum and product, which are really implementations of that sum and that product, okay, using this one operate function. Okay, so we have generalized the plus and the multiplication into a function, and then we are passing that value as a parameter. Okay, and then this main program is just to print. Oh, by the way, this is how you do print line in Scala. There's no system.out.println, just print line. Okay, sum of 1 comma 6, and it'll print 21, and then the product of 1 comma 6, which is the factorial of 6, will give you 720. Okay, so that's a different way to, not different way, a different generalization of the summing and the producting. Okay, in the earlier case, we were actually only summing, but we were summing different functions operating on the values a through b. Okay, here we're not talking about the functions themselves, but we are functions which modify the a, but we just either adding or adding numbers or multiplying numbers. Okay, and we generalize that. Okay. Oh, by the way, this is how you call a method inside. For example, here the main method. Okay, that's the main is a method or a function. Okay, inside the sum product. So sum product dot main, and you have to provide some arguments. Okay, but since we ignore all the arguments, you can provide an empty array. So by the way, that's how you instantiate an empty array. Now, but arrays and all are coming in Scala 4. The fourth part. It'll come at the last part of this Scala section. Okay. All right. So that's the sum product example. Now let's talk about currying. Okay, this is another important concept in functional programming. Okay, and that is that if you remember, lambda calculus imposed the restriction that you cannot have more than one parameter in a function, right? Lambda x dot, you cannot have more than one. Whereas programming languages like Scala, JavaScript, and so on do provide multiple parameters. Okay, but we still need to understand this concept of restricting to one parameter, or even not necessarily one, but maybe two or something like that. Okay, so we do want to understand this currying concept. Okay, I mean, when you start using it, becomes pretty straightforward, but the notation and the theory behind it seems a little tricky at first glance, but actually it's not. Okay, so let's try to figure out what is currying. Now, by the way, currying is not a normal verb. Curry is the name of a person, okay, just like Steph Curry. I think there was a Haskell Curry. You see, now Haskell was a famous mathematician in the early 1900s, I think so. Okay, and his first name was Haskell. His last name was Curry. He did have a middle name. I forget what it was. Blake, not I forget. Okay, you can Google that. Okay, so he's got a middle name as well. Okay, and he's such a unique person that each one of his names, first name, last name, and the middle name, became common nouns eventually. Okay, so Haskell itself became the name of a programming language. Okay, Curry has become the name of this operation. Okay, and then the middle name, I forget what it was. Let's just assume it's Blake, but I think something else. It starts with a B, I think so, but it's not Blake. But the middle name also became a programming language. Okay, so this guy is really, really famous. Okay, Haskell B. Curry. Okay, but anyway, the currying is an operator. Okay, or it's a trick or a technique. Okay, a technique of reducing parameters. Okay. Okay, so let's see how this goes, or how we can explain this. Let's recall these four definitions from the first version of that higher order functions. Okay, sum is not the first version. This looks like the second version, you see, or the third version, the version in which we generalize the function of cubing and factorial and so on. You see, so you can see that in the body here we say we do provide f as a parameter. Okay. And then the a and the b, okay, and then we apply f here, okay, and then in the sum ints, sum cubes, and sum factorials, we provide this as the value of f for sum ints, this as the value of f for sum cubes, and this, assuming that there's a name. Oops, I double click that. Okay, assuming there's a name called factorial for the factorial function. Okay, that's provided here. So these are the three values for f. In that. Okay, so let's look at the sum function. Okay, the first one, the f, a, and b. Okay, now if you look at this, the a and the b parameters are actually not used directly in the body. You see, they just passed on as values to f and to the sum. Can you see that? This a comes in as parameter, and then it's not used directly, it's indirectly. Okay, it's passed as a parameter to f here, and then I guess sort of directly it's used a plus 1 here. Okay, but it does go as a parameter into. Now a does not change the value because it's all called by value, right? So a new value is computed for a plus 1. So that in that sense it's indirectly used here. Okay, a plus 1 is sent here, and then the b is sent here as it is. You see. So the point is that the parameters a and b get passed on to sum and also to f without any modifications. Okay, and whereas the f, the third parameter f, is actually used in the body here. You can see that f, it's also passed, but it's also used here. Okay. Anyway, that observation indicates that we can sort of really get rid of a and b as parameters in sum. Okay, maybe we can push it to the something else. Okay. Got it? And this is the general idea of currying. Okay, so here is an attempt. Okay, right here in the middle here. Let me highlight it here. Okay. All right. So we are. Our intention here is to sort of get rid of the a and the b in sum. Okay. So that's what we do. Def sum, and we provide only one parameter f. Okay. F is that function which is the cube or the ID or the factorial or whatever it is. That's the function. Okay, and say that that's all we have here in the sum. Okay, but in the output, okay, instead of previously we were returning an int as the output here. Okay, correct? Here you can see that. I hate it when I double click and it goes into that cell. But here you can see that the output was an int. Okay. In the previous version of sum. Okay, but now because the a and the b are not coming as input, what I say is the output of sum is not an integer, but it's going to be a function. Okay, got it? Now functions, this is the first time we are seeing a function as an output. Okay, I did say that in function higher order functions can be input parameters. They can also be outputs. Okay, and this is the first time we are talking about functions as outputs. Okay, and the highlighted portion here, int comma int arrow int, is a function. It's a type of a function, right? Data type for a function. What type of function is it? It takes two integers as input and produces an integer as output. Okay, it doesn't tell what it does. Okay, it doesn't say it adds them up or multiplies them up or factor whatever. It doesn't say that. Okay, it takes two integers. Okay, and then produces something. Okay, it produces an integer as output. Okay, and our intention here is that the two integers which are as input to this function will be the a and the b. Okay, the two extremes. The a, the left extreme, and the b, the right extreme in this particular problem. Okay, and the output is going to be the final answer, which will be the a cube plus a plus 1 cube plus a plus 2 cube and so on up to b cube, or the final answer would be a factorial plus a plus 1 factorial plus a plus 2 factorial up to big factorial. Okay, or it could just be a plus b plus c, a plus 1 plus a plus 2 up to b. Okay, so the output will be the final answer we are seeking. Okay, so this function, which is sort of not parameterized, but it is becoming output of the sum function. Okay, is the function which actually computes the final answer for the original problem. Okay, got it? And this f is the cubing factorial function or whatever it is. Okay, so instead of providing a and b as parameters here, we are actually forgetting about that, and we are postponing it in some sense, and we're saying that let the body of this sum function take care of that. Okay, and you can see that the body of this sum function must return a value which is a function. Okay, which is that another function which will take two numbers as input. Okay, a and b as input, and produce the final answer as output. Okay, got it? So that's the function we have to define. Okay, so let's see. Now you see that I started a block because we are going to do two things here. We're going to define a function, and we're going to return that function. Okay, I hate it again. Okay, we are here. Okay, so we're going to define the sum f function inside the sum. Okay, and that function takes two inputs a and b. Okay, which is the signature shown up there. Okay, and returns the integer as output. Okay, and what does it do? Now it can access f and a and b, everything in the body of the sum f. Okay, so scoping rules will allow you to access f as well here. Okay, because f came as input to the sum, so automatically it becomes available in the output of sum. Okay, which is the body of here is available here. Okay, and the a and b comes as input to sum f. Okay, so it's available inside the body of sum f. So inside the body of sum f, f, a, b, all three are available. So that's why this line of code, which was there originally, okay, remember in one of the earlier versions we had this, we can write here without any scoping issues. See, so these two lines, def sum f and then the if statement, those two lines define a function called sum f, which takes f as input, actually indirectly. Okay, it is available here, and then a and b as input, direct inputs, and produces the final answer based on this formula there. Okay, and then we say sum f here because this sum function is supposed to return a function which will be the sum f function. Okay, seems complicated, but if you get used to functions as values, it's not. Okay, got it? Because the sum f is a function value. Okay, and that's what we return here. And what is the type of? So the one thing you have to be always careful in functions as values is the types, data types. Okay, because function data types are a little bit more complicated than integer data type or a double or a boolean or a string. Those data types are simple enough, right? They just have a name. Whereas in function data types also have not names, but they have a signature. Okay, that's the data type. Okay, something arrow something. Okay, the input types and the output type. Okay, that's the only cause for confusion. But if you can overcome that cause for confusion, then this becomes routine stuff. Okay, Functions also have types, data type, just like numbers have types. Okay, and booleans and values have types. Functions also values, and they have types. Okay, all right. So that's this next version in which we are using the concept of currying. Okay, now why is it currying? Because the top function has only one parameter. Originally there were three, but it's we reduced it to one, called f. But the second and the third parameters are required as input for the inner function. Okay, now let's see how to call these. Okay, so that's the once we understand how this curried function is called, then I think everything becomes clear. Okay, so let's look at currying and how to call it. Okay, or before we actually call it, let's define our sum. Remember, so far we have not done the sum ints because we have not provided a value for f yet. You see, so this sum new version of sum function, we can use that to create sum ints, sum cubes, and sum factorial functions as follows. Okay, def sum ints equals sum. Okay, this new version of sum, and it expects a function, right? It expects a function as input, the f, which is the id function in this case, x arrow x. Okay, so that becomes the value of this f, and that's all it expects, only one parameter. It doesn't expect the a and the b here. Okay, got it? So when you call sum, you have to provide only the f. Okay, so for sum cubes, it'll be sum of x arrow x cube, x times x times x. For sum factorials, it'll be sum of fact. Okay, now the reason we just have fact and not an anonymous function is because factorial could not be anonymized. Okay, so those will be the three names with this new version for these three functions. Okay, what are these three functions? They will actually do the job. Okay, so now we could actually call sum cubes as follows. Okay, this is how you may call it. Okay, sum cubes, and then you provide sum cubes is the function which already has taken x arrow x cube as the f value. Okay, so this sum cubes is already has the f value, the cube function built into it. Okay, and then when we call it, because the output of sum cubes is actually a function, right? Sum cubes is actually a function which takes two a and b as inputs and then produces a number as output. So that's why sum cubes has to be called with the a and the b. Got it? So here are the two steps. First step is to call sum with f. Okay, to get a function called sum cubes, and call the sum cubes with a and the b. Okay, so this is how you separate the f from the a and the b. Okay, and this is the concept of currying. Okay, you're currying, that is, instead of having three parameters f, a, and b, we are sort of breaking this process into two parts. The first part takes only f as the parameter. Okay, and then the output is a function. Okay, and that function takes two parameters a and b. Okay, so you're sort of breaking the whole process into two parts. First to deal with the first parameter f, and then after that to deal with the a and the b, separating. So you're separating them out. Okay, so this is how you can call it. And similarly, some factorials can be called with 1 and 5. So it'll add the factorials of 1 plus 1 factorial plus 2 factorial and so on. Okay, now there is a further shortcut. Okay, because of the anonymization or actually not anonymization. Yeah, that's right, anonymization. You really don't have to give names, intermediate names. Oops, some ints, some cubes, and some factorials. You don't have to. Okay, you can directly call sum. Okay, so these are called the middlemen. There are some int and some cubes and some factorials. Those three can be avoided by just calling sum of cube. Okay, in parentheses cube. Remember, cube was the name of this function. Now this cube can be replaced by x arrow x times x times x if you want. Okay, so cube was already a name, so that's why we did that. Okay, but you could always replace cube by the anonymous version. You see, x arrow x times x times x. Okay, and then you can provide in parentheses the a and the b. So you can see that it's now we are cascading the call. Okay, sum is that the generic function. Okay, it takes only one parameter, so we call f. Okay, and we provide the value of f, which is cube, And then the output of the sum cube is actually a function which takes two numbers as input. So that's why you see 1 and 10 here provided. And that whole thing expression will provide the final value. Okay. So if you wrote a function like this, you need to know, because there is a function application here, one followed by another. Okay. The associativity is left associative. So that's why the sum cube 1 comma 10 is really this expression here. Okay. So you'll have to apply apply to cube first, okay, left associative, and then you have to apply it to 1 comma 10. Okay. By the way, we have done stuff like this in lambda calculus. Okay. So it's all the founding blocks of this part is all lambda calculus. Okay. All right. One last thing in currying concept, okay, is there is a remember in this previous version we had this version for the generic version for the sum, where we took the f and then the int and the thing, int comma int arrow int is the output, okay, and then we defined the sum f function and then we return the sum f as a value, right? So that's generally how. Now this whole thing, because it's done so repeatedly many times and by all the programmers, there's a shortcut notation which has been introduced in Scala, okay, and it's called a special notation in Scala, okay. So, and it's important to learn this, and actually it's fun and easier. It makes life easier with this notation, okay. But this is actually a special syntax notation, okay. So we are looking at that next the sum f version, the version where we name the function and return the sum f, okay. And we are rewriting it with this special syntax. So def sum, and this part is the same as before. F is a function int to int, okay. And then in the previous version we had colon, and then we returned the function type, and then say equal, and then we had the block in which is the sum f and so on, okay. But that whole thing can be compacted by, because if the output is a function, you might as Scala provides the ability to put another set of parentheses, okay, and list the parameters for that function which is going to be output, okay. And then so in that case it will be a and the b, right? So you can write a series of parentheses expressions next to the function name, okay. This is actually the effect of currying, okay. So you're separating f from the a and the b, and finally when a and b are provided, the final answer must be integer, correct? And this equals, and if a greater than b then 0, else f of a plus sum of recursive call again will be done with the same notation, you see, with the two sets of parentheses for that cascading, okay, of separating the f and the a. If you remember, originally it was f comma a plus 1 comma b, but now we are separated f from a plus 1 and b, okay. So this is a special syntax available in Scala, and this is what we'll start using instead of that returning a type a function as an object. Okay, here also we're actually technically returning a function as an object between these two calls, okay. But so this shows for a specific example with 1 and 2, 3 parameters, okay, separating the 1 from the 2 parameters. But in general, we can write a function like this, okay, def f, and then you can have one argument in parentheses and then a parenthesis with another argument. So instead of saying comma comma comma, we'll say parenthesis argument 1 plus parenthesis argument 2 and so on, and this is really the currying notation, okay. So if you had 5 arguments, we are breaking down this into 5 parts, you see. First part takes the first argument, the second part takes the second argument, and so on, okay. So that's what this is, and when n is greater than 1, this whole thing becomes equivalent to like this, okay. This is the block, and you take the last argument and define a function and give it a name g and call it e, and then return the g, okay. And then you can take this new function, okay, and then simplify it one more step, okay, and you can repeat this n times, and finally you'll get the value of f, which will look something like this, okay, which is technically what we were trying to do in currying. We take the last argument and as separate it out, okay, and provide that as input, and then e becomes the output for that localized function down there, okay. All right, then take the arg n minus 1 as the input and provide this function as output, okay, and then go backward one step at a time until you get this long function here. Okay, so this is a very interesting function. It takes one argument and returns a function which takes one argument, which returns a function which takes one argument, and so on. Okay, and the arguments are successive 1, 2, 3, 4, and so on until the last argument is received. Then the output is e, okay, which is the original body of the function. Okay, so this process of taking n parameters and separating each one out as an individual argument and a single parameter. Okay, and this is really what lambda calculus is all about, right? Remember, lambda calculus, you're restricted to one argument, and here is an expression which converts n arguments into one argument. Okay, and this process is called the currying process. Okay, and when we start using it, it'll look like this. Okay, so things like that. Okay, or actually here. Okay, this is how we start using it. Okay, and this is how we might define it. Okay, where's the definition here? Okay, so here, this is how we will define curried functions. Okay, by separating things out. Okay, in this case we separated f from a and b. Okay, but in pure currying you'll separate f first, and then you separate a, and then you separate b. Got it? So three-step process. But here we just showed two steps where we separate f from a, b. Okay, all right. One last thing before we go to the next topic, and that is once you have, we are almost 36 minutes, so let me explain this type, and then we will stop this set of this second video. So when we have a function of this type, let's say this is really what we have. F is sum, and then f is the first parameter, and then the cascaded one a and b. The question is, what is the type of this sum? Okay, if something like this is given, the type would be this f is int arrow int, right? So that's this here. Okay, and then this returns a function which takes two ints and then returns one output int, right? So the a and b as input here, and then the int as output there. So this will be the final answer. And also this this one associates to the right, the arrow greater than. Okay, so if you do want to parenthesize, you'll parenthesize the right one first and then the left one. Left one is not necessary because there's only this already parenthesized, so there's only two arrows here. So this is a parenthesized first, and then so the final type would be a function f comes as input, and then the output is a function which takes two numbers a and b as input, and then integers output. Okay, all right. I'm going to stop this video here, and I'll be back soon. Take care.